Okay, guys, let's pick back up again where we left off. Okay, okay. So I said last time I wanted to trade places. So let's write this as y equals x squared minus 6x. But now we want to get the inverse equation. Let me just write the constraint here too for the original. Now with the inverse, what do? We do x equals y squared minus x and y literally trade places. X equals y squared minus 6y with the understanding that y is greater than or equal to. We have a big trade in the places here. So we traded places. Okay. Well, ooh, we got to solve for this guy, right? So how do we do that? Well, we have to complete the square and stuff. Y squared minus 6y. We need to add 9 to that to make it a perfect square. So let me add 9 to both sides. X plus 9 equals y squared minus 6y plus 9. But remember, so we have x plus 9 equals, this is a perfect square here. This is namely y minus 3 squared. And but with the stipulation that y is at or above positive 3. So we, because of this right here, we adopt the positive square root. We got to keep y. We got to, if we were to subtract 3 from both sides, what's that say? Notice right here, that's the same thing as y minus 3 is greater than or equal to 0. So y minus 3 is positive. Oh, so that means x plus 9, we adopt the positive square root here. So the positive square root of x plus 9 is y, since y minus 3 is positive, we do this positive radical. X plus 9 is y minus 3. Then we add 3 to both sides. Be sure don't put it in the radical. What I like to do is just put a plus right here, put that 3, and that will give you y. But notice that the y that we have now is what x used to be, and vice versa. So, but this y is not f anymore; it's f inverse, right? Or particularly, it's g inverse because g was the old thing, so it's g inverse, and that doesn't mean reciprocal; it means inverse. Be careful. Um, there it is. Yeah, and here natural log and e and all that stuff. You just trade places. So x equals. Notice that y by nature is going to be greater than 0 strictly. So we trade places. X is going to equal e to the 3 minus y. Now x is going to be greater than 0. And what we do is we take the natural log of both sides. And like that. The reason we do it is to so natural log and e kill each other. So yep, they will. So what happens is natural log of x equals ln and e kill. We get 3 minus y. Let's do, so yeah, that's great. So, and if I add y over, that would be ln x plus y equals 3. If you don't like negatives, then subtract ln over. What did I do? That's 3 there, right? My bad. And then subtract ln over, and that would be y equals 3 minus ln x. You just have to be careful. Basically, remember when you're inverting what you're doing, since X and Y trade places, you're reflecting about the line Y equals X, the 45-degree line. Your mirror reflecting about it that you're always doing. We talked about that last video. Just trade places with X and Y. You'll get there. It just gets ugly sometimes. Now here, Y can be all real numbers. X has to be greater. Notice X, though, has to be greater than 4. Otherwise, the natural log will be undefined. So here we trade places, and it's going to be Y that's going to be greater than 4. Because it's going to, we're using the invert equation. We're going to solve for Y to get the inverse. It's the same idea we've been doing before. We divide by 8. You got to get the ln by itself, right? Now remember, you can exponentiate inverse style, sort of going the other way, because you already have ln. You need the other guy, so you need E. So do it like that. That E and that ln will kill each other. So that, notice it's understood that Y is better than 4, but anyway. So we get E to the X over 8. We can't really cancel anything there. Right? It's equal to Y minus 4. Oh, that's the prize egg. Y came down. We add 4 to both sides, and we get what we want. E, Euler's E to the X over 8. Then plus 4. That's a vertical movement of 4 upward. That equals Y, which is, of course, that's going to be the inverse of the old function. The old Y is the new X and vice versa. There it is. You know, now log 2 of 16. Remember, 2 to what power is 16? 4. You can also do it this way. Well, you got to sort of, you can punch in your calculator, but the idea is function inversion. Log 2 and 2 to the X kill each other. 2 to the 4th, 2 to the X. So they just kind of kill each other. Oh. Log 2. It's not being very flexible. 2 to the X. Bye-bye here. Bye-bye there. And you just get X, right? That's an equal sign. Oh, it's an ugly equal sign too. That's an equal sign, I promise. Okay. For the this is neg 4. 2 to the neg 4 is 1/16. It's like BOA. B to the O equals A. And 64 to the 1/6 equals 2. 64 to the 1/6 power. Remember, that's the 6th root of 64 equals 2. Right? That's why that is true. Now this looks right here hard to digest, but what's this saying right here? It's E to the ln. You can just use parentheses here. E to the ln 4 close parentheses cubed by the laws of algebra. That's just this times this, but it's better this way. And I got ink right here because that's just E to, well, that's just plain 4, so it's 4 cubed. That's just 64. And I do the analogous thing here. That would be 3 to the power neg 4. 3 to the neg 4 power is 1 over 81. For that part. Now for this part, ooh, it's kind of nasty, right? But not really. Let's check it out. E to the ln of the ln. Well, it only seems nasty, maybe. E to the ln of the ln of E to the 8. Well, close this one from this one. This one demands another one. These kill each other. and we get e to the ln 8, but then these kill each other. It's just 8. Okay, that's cool. Now remember the logs, as long as everybody on the inside is positive, and that's a biggie, right? Like if you've got big A positive, big A greater than 0, you got big B the same thing, greater than 0. Then any log, it could be the natural log, but any like natural log of any positive based natural log of AB the log of the product is the sum of the independent logs. So let me go down here. So that equals log base P, P is in positive base, of A plus log base P of the other, well, B. Notice it's a product in here. It's times. We're timesing, but out here we're at. That's but anyway, and the exponent, we also have the exponent. Remember the exponent rule? So for a positive log, like if you have positive x variable raised to any power, any real number r can be negative. It can be 0. It can be whatever. That equals r times just the basic log, the log p of x. The r came down and multiplied. So what we do, you can combine these. You can bust that up. So the log base 10, you bust this guy up first. So it's the log base 10 of x cubed plus the log, it's the same base, log base 10 of y to the 4th plus the log base 10. Your calculator log writes log base 10 is just log of z. Now, by the other rule, we can bring that 3 down. So it's 3 times log base 10 of x plus 4 times log base 10. Log base 10, I'm going to leave it just barren because it's understood. It's the only one that is. You can't do that for other logs, okay? Y, and then plus, well, we don't really have the other guy. You just leave him as is. There's not much to do. So now, if you divide, you subtract. Dividing leads to subtracting in the analogous way. So the positive log p of a over b is going to, well, that's going to equal log p of a minus the log p of b. And that really follows because the log of the reciprocal is the negation of the log of the original. Like the log of 1/7, any log of 1/7, like the log of 1/7 is the negative of the log 7, for example. Okay. So with that being said, you just break this up. Now, natural log is log base e. P equals Euler's e. Right? So we have natural log of x to the 6th. And x has to be greater than 6 in order for this radical not to go square root negative on us. And then minus the natural log of, well, this is kind of ugly. We have one layer of parentheses, and we have a square root of, now x squared minus 36. That is going to be x minus 6 times x plus 6 by factoring of algebra. So yeah, that got a little ugly. Pulls that off. Now, what I can do straight away, I can bring that 6 down right there. So it's 6 log x. Now, that half comes down. So that's just, that square root is a half power. So minus the 1/2 natural log of the product. You'll need another layer for the x minus 6. Another layer for the x plus 6. We're doing the natural log of all of this whole product here. Notice the square root's gone because I took it out as a half right here. Well, so that equals, we got 6. Here, it's right here in the middle. So we got 6 natural log x. That just is what it is. It's just there. It's not going to go away. It's just not really going to affect the mechanics much. Now, remember by the bust-up rule, minus 1/2, then x plus 6, minus 1/2, that negative half is there to stick on. Then x minus 6. Now, domains. This first guy here says that x has to be greater than 0. You want the interior to be positive. This second guy says that x has to be greater than -6 to keep that interior positive. This third guy says that x has to be greater than +6. But we've got to obey the one that's the fussiest, the one that's that's the most restrictive. Well, that would be x greater than +6. If you're greater than +6, you obey all the others by default. So this is the one we adopt. Greater than +6. Well, and now you can go the other way. If you contract, you can contract in, right? So what you do when you contract in, like you take that x minus 4, raise it up as a 5, and well, you, let's see, that minus sign, let's bring it all together. Oh, maybe not. Let me go ahead and dig it out. What are we minusing? Minus the natural log. Now this can be factored as x minus 4, x minus 5 inside the log right here. Close and another close. Now this guy right here plus the natural log of, now that square, we're going to, it's going to be the natural log. Remember, you do one layer, you square the x minus 5. Now guys, never square the log. Never power, or in general, never power the log. Like here, we only fifth powered x minus 4. We didn't put the 5 out here and fifth power the whole log. That'd be a mistake. Okay. Just careful about that. So x minus 5 squared like that. Now we can bring all this together. So natural log of, now that minus means denominator. So we're going to have a x minus 4 parentheses down here. That x minus 5 comes with it. Now, this x minus 4 to the 5th is up here because it's just positive. Now, that x minus 5 squared is up here. Now, notice down here we have understood 1 power, 1 power. We do algebra 1 and 2. Let's see. We do 5 minus 1 is 4. So that would be x minus 4 to the fourth power right there. And for x minus 5, 2 minus 1 is 1. That'd just be x minus 5 to the first power, x, which is just plain x minus 5. So inside the log, we'd have this guy right here. You need the double layer parentheses. Don't leave them out. Now, change a base. Just use your calculator. But what they're talking about, change a base goes like this. If you want to go from one base to another, like if P and Q are both positive, like you can do this. The log P of X equals the log B of X log B of X over, I better be careful. Okay, so the log base P of X would be so if this over here was like the log base 2, if you just think, so if this were log base 2 of X, natural log of X over natural log of 2. So you want to be, if you have a B here, you always want the B here. The P acts differently over here. It acts like an argument. So this is the change of base formula. So like, for example, if you do the log base 7, if you put a 7 here, put a 20 here. Well, let's just say you want to use the natural log. E as in Euler would go here, right? And here. So you'd have natural log here, natural log here. So you'd have the natural log of this is still 20. We're defining x to be 20 in this problem. But this formula is valid no matter what for many things. But we're doing this example now. Now we're defining P as in positive, naturally 7 right here. And now B is Euler's E. Remember, E is about 2.7182, remember? So we got that. So there we go. And you can change these. This is the same thing as ln. Log base E is the same thing as just ln. So you have ln of 20 over ln of 7. I've messed this thing up good now. So the general form is what I had 2 minutes ago. I wonder if I could ever go back. I mean, I did mess it up, but it was, so what I said was right, but this is the general form, right? So put your 7 here, that's dandy. 7 here, that's dandy. You can make x 20, and that's dandy, but this is just a specific example. The beauty of what I had a minute ago, Euler here is dandy, Euler here is dandy. But this is one example. I like to have the general form. So you can hit Control Z, just go back to the general form, which is all this right here. This is the change of base form. And now you can just use your calculator to do this. I can tell you the log 10 is increasing. I can tell you a plus 2 is a leftward shift. It would be this guy right here. But it's increasing, but it starts to slow down. We're going to call that, we're going to call that concave down later. Frowning kind of graph, but more on that later. Now part B, ln of x flipped about the x-axis. That would look like the last guy here. That would actually be, as you go rightward, you're decreasing. We always go rightward. We're decreasing. Number 12, solve each equation for x. Yeah, you Euler both sides. E to this power equals E to that power. So so E to this, E kills the ln compositionally. Not multiplicatively. When I say they kill each other, I'm always talking about composition. So e to this equals e to that. But these compositionally kill. So it's 4x plus 5. I don't need an equal sign yet. So 4x plus 5 equals e cubed. E cubed is just a number, right? That's all e cubed is. Solve for x, subtract 5 from both sides. You'll get e cubed minus 5. Divide e cubed minus 5 by 4, or multiply it by a quarter, 1/4. Same thing. You'll get that. If you round it with a calculator, you get that. The second guy, you'll stick a ln on both sides. Right? Ln of this guy. Sorry. Equals ln of 18. Ln of 18 is saying e to what power is 18? But now these kill each other. So it's 5x minus 4 equals ln 18. And you just solve for that, you'll get this. You round it, and that's just, these are, decimal approximations. You get that. Now, if you want the inverse of something nasty, like this guy right here, and that's nasty. The best way to write this guy is 80. So it's 2 times t to the 1/4. So f equals f of t equals 80 times. Now, yeah, that's all well and good, but let's just go ahead and call it what it is. That's let's just go ahead and turn 2 into e ln 2. I'm going to sort of go counter backwards, right? I'm going to go turn 2 into e to the ln 2. And then I'm going to put my t to the 1/4 t out here. Why do you want to do that? Well, I got my reasons. So that's 80 e to the power of, well, that's, you can write this, put the 4 down that bottom exponent denominator. You've got t ln 2, right? So it's t. Okay. Well, no, this ain't perfect, or this is not perfect, but it's better. And what I can do now is, so I can just sort of treat that as my y if I want to. So treat that as my y. And I'll let y and t trade places. Instead of x, I've got t. Just let y and t trade places. Um, so, well, if I do that, it's going to get a little ugly, but I'm going to notice that y is greater than 0. So the same thing is going to be true of t. So t is going to, I'm going to get my inverse equation, which is always different than the original. But we're going to solve for y, put t and y in the correct places. So we put y here, just doing the inverse like I've been doing. Over 4, and this is all in the exponent, right? Sorry if it doesn't look that way. Well, what have I got here now? Why would I want to do this? Let's just see. How can I rewrite this maybe? So that would be 80. So this would equal 80 e. Well, 80 times, what do we got here? I want to isolate that ln 2 real bad, real bad. I want my e to the ln 2. Yeah, yeah, I do, don't I? Well, I've got e to the ln 2. You know what? That didn't do. Me doing that, was that a waste of time? Shouldn't I just did I really do us any services here? I've not done anything wrong, guys, but is this really fruitful? Count my losses. Is this pedagogically fruitful? No, it's not. Um, I don't think so. No, I think I'll be fine. It'll be all right. I'll stay with this. It'll be all right. Let's just do this. So, let's forget about this. Oop. And forget about this. Forget about this. I didn't do anything wrong, and I knew I didn't, but I didn't know if I'd been pedagogically friendly. So we have this. I just need to divide both sides by 80. We did our, this is my inverse equation. I divide both sides by 80, right? And I get t over 80 equals e to all that junk, right? Y ln 2 over 4. Now I take the ln of both sides. I have another ln that I got to use. That's a little bit ugly, but it is what it is. So I'm gonna come over here. I'm all over the place, but it's just is what it is. So I probably could have done better with that. So the ln of t over 80. Try to make my 80 not so ugly. So the ln of t over 80. I'm finding it hard to do. So the ln of t over 80. So take the ln of this side. Now, if you take the ln of this side, remember ln and e kill each other. You just get straight away. Y ln 2 times 1/4, or we could divide by 4. Well, if I multiply both sides by 4, that puts a 4 up top, right there. And if I divide both sides by ln of 2, that puts the ln of 2 down there. Well, so there I go. But no, one last thing. So I'll have 4 ln t over 80 inside the ln. Then divide that whole thing by the ln of 2. That will equal y. But now here's the thing: we replace instead of t's the whole time. I should have been using n, but that's okay. Just go over here and replace t with n. So everywhere you see a t, just substitute an n. So put an n here where a t is, n here, here, and here. So on everywhere you see a t, put an n, because when you do the inverse. Wait, no, not right here. Right, yikes! Not right here. Sorry. That would be a mistake. Sorry. The original, that's not going to happen. Don't mess with the original. In the inverse, you won't use it. So n right here, n right here, not right there, because that's the original y. It's n is in the inverse. Letter n is in Nebraska, goes in the inverse. Right here, right here. I forgot to change my t's to n's, but should be okay. And there, you're all set, right? Replace t with n. Okay. Now, arc sine and arc cosine of trig. Yeah, this is a lot of review at this point. To get the arc functions, you have to strongly restrain the sine and cosine and tangent to get the inverse sign. This does not mean reciprocal, by the way. Careful. The reciprocals are something else. They're like the secant and tangent, secant, cotangent, and cosecant. That's a different animal. These are not reciprocals. These are the inverse functions. Neg1, unfortunately, does not, in somewhat of an abusive notation, this does not mean inverse, alas. If you go backwards, the arc sine of this is the angle that gives you, such that the sine of this angle would give you, so the sine of neg pi thirds, which is negative 60 in Babylonian degrees. So the sine of neg 60 degrees is negative 1/2 of radical 3. If you went backwards, it's the it's the angle between it's the angle on, we restrain ourselves to the arc sine has an output. Well, let's do input first, or output. No, output of the arc sine, or the inverse sine. We call it arc. Inverse or arc sine has an output. Now, these are inputs for the regular, but they're outputs for the inverse. So these are range. This is the range of the inverse sine, right? This is the range of the inverse sine. Let me. I need some room about this. So this is the range of the inverse sine, and the domain is neg 1 to 1. Well, the domain is kind of obvious. You remember the sine can't spit out anything beyond neg 1 to 1. So you could, as far as output, so you wouldn't expect the input of the inverse to be different. So this is the domain. Now, that's for the arc sine, right? Now, for the arc tangent is a lot like the arc sine. The arc tangent, it's fairly similar, sort of, kind of, except it's opening. You put parentheses here, and, well, but now there's differences. I need to be careful. My tongue may get bit. This is the range. Now the domain is going to be darn different. The domain is going to be all real numbers. Domain is going to be, wait, I better be careful. Better be careful. Well, that's only true of tangent. No, gotta be careful. Gotta be careful. This is the range. The domain. So my arctan, what does it look like? Let's just come on back. So we have this red graph here. Yeah, here's the arctan, guys, here in red. And maybe I needed that phone call. It distracted me. Made me sort of really spend my attention out. F prime of x. The graph of f prime of x, my slope is never 0, ever. Notice my green graph, if my slope were 0, the green graph would hit it. Notice my slope is always positive. So for arctan, my slope is always positive. So that's the 10. So the green gives you the slopes. If you want to know what that function is, by the way, it's y equals, I'm not justifying that why it's true. It's y equals 1 over x squared plus 1. But that needs justification, but more on that later. But from pre-calc, yeah, notice you can tell the slopes are always positive. As you go right, you're going up. Your slope at the origin is 1, by the way. I can kind of tell. Your slope actually goes to 0 as you go toward neg or plus infinity. Like f prime of 1,000 would be darn small, 10 to the negative 7th power, or 10 to the negative 6th power, or something. Well, so that's the arctan. I should have used Desmos all along. My bad for not doing so. Now let's just blot these out for a minute. I didn't really mean to get rid of them. I can bring them back. Okay. Let's just blot them out without getting rid of them. Let's do g of x or whatever, and let's call it the arc sine. Now that's not reciprocal. And now the arc sine is restricted, notice, by vertically and horizontally. G invert of x. Well, now here I'll need to get, what's the inverse of that look like? Well, it's the sine, but we're talking about that. What about the slopes of this guy? They are always positive. And actually, it gets infinitely steep as you get to the endpoints. So yeah, I was getting my arc sine kind of conflated, my arc tan conflated with my arc sine. Sorry about that. So there's that. The slope gets infinitely negative as we go here, and infinitely positive as we go here. The slope at 0 appears to be or equal to 1. That's where the red graph is. Indeed, that would be true. I've not really told you what G prime is. It would be, it's 1 over radical 1 minus x squared. Again, I've not justified that at all. More on that later. Now, finally, let's do h of